Yeah, thanks, Earl. That is what I'll be talking about. And yeah, I'm very happy to be here back in Sydney, and thanks to the organizers for putting together a great conference. It's been great to hear all these talks. Yeah, so this is joint work with Shilin Huang, who was an IBM intern and at the time was a PhD student at Duke, and now has moved on to a postdoc at Yale, and Ted Yoder at IBM. Okay, yeah, as Earl mentioned, I'll start with this main bullet point. The main question we're trying to address here is how to perform fault-tolerant logical computation. Okay, this is quite a general, large question. Kind of maybe more precisely is what we're going to be addressing in this work is how do we perform targeted fault-tolerant logical computation in higher rate codes. So we've heard a little bit about these codes throughout the conference. It's exciting as, in the last few years, we've been talking more and more about how do we get higher rate codes, that is codes with a larger number of logical qubits. And it's going to become important to be able to do addressability of each of the logical qubits. So we know in general, like if you have some CSS code, you can just do a transversal CNOT gate. And what that ends up doing at the logical level is does a transversal CNOT gate at the logical level, which could be great. But we also want to be able to do CNOT gates between different qubits, for example. This is going to be kind of one step along that path. And there have been other works that have addressed this issue as well, and I'll highlight them shortly. Yeah, so this work in particular will be a way to do this that's an approach that's based off the techniques from old fault-tolerant techniques of Shor and Steen error correction. We're going to be focusing on doing logical measurement, but how that relates to computation could be nicely understood by this circuit diagram, which I think came from a paper by Kiran and Andrew, where you can do, with one auxiliary qubit and joint XX and ZZ measurements, you can perform a CNOT gate between two qubits, and this can be done at the physical level, but also can be done at the logical level, right? So this is how measurement relates back to computation here. Okay, so this is probably an incomplete list, but there are many different approaches to doing logical computation. I've kind of summarized them in 4 big bullet points here, but there are more than this, and these have been widely studied. If you have attended the previous QECs over the years, there have been many talks on many of these topics, and there have been attempts to and very nice work on how to generalize ideas from these bullet points into higher rate codes. I just want to kind of summarize some of these results, and this is not an exhaustive list. I am sorry if I missed out on some works. But one in particular that caught our eye that we found very interesting and is appropriate to talk about here is from the University of Sydney group. And here, their idea was sort of like a code deformation or lattice surgery type approach to this, is that if you have some Tanner graph which encodes your code, and you have many logical qubits that you can describe in this Tanner graph, what you could kind of end up doing is you might have some logical string or logical representative in the Tanner graph, and you can kind of bring in this sort of surface code patch and stitch the surface code. The way I like to think about it is you stitch the surface code patch to your Tanner graph, which encodes your logical information, and then you teleport the relevant information from your data qubits onto the surface code patch, and then you read out the surface code patch. It's a little more complicated than that, but that's kind of the high level essence of it. And what this technique allows is it's very flexible. It allows you to kind of measure almost arbitrary sets of logical operators, and there are some caveats, but kind of some of them, and I'll come back to comparing our result to their result. Their result is a little bit more flexible, but there are some caveats about, you have to change how you're doing decoding, because now you have to decode both the data qubits and the patch at the same time. And you have to do this kind of in an online manner. And we wanted to push our technique to an offline, where you prepare some resource state offline, and then you can do everything kind of in a single shot manner. Okay, so that's just a contrast to there, but there are many other works that have addressed doing logical gates on higher rate codes, and I've highlighted some of them here. Okay, so here's the general structure of the talk. I'm going to kind of spend the first half reviewing old results and kind of summarizing Shor and Steen error correction for those of you who might be less familiar with it, and pointing out some of the caveats with those techniques. And then I'll be spending the second part of my talk discussing our homomorphic logical measurements, the definition of them, and then how we can come up with a few examples of how they can be useful, and primarily focus on the Tor code, but then generalizing to 2D topological codes. And then I'll discuss at the end kind of some comparison and open questions. Okay, so when we're talking about doing logical measurements, we do them all the time. In fact, when we do a stabilizer measurement, you're actually doing a measurement of one of the representatives of your logical identity gate. And so there have been many works over the years that have carefully constructed how you do these stabilizer measurements in a fault-tolerant manner. And of course, one of the examples, which was even brought up in the last question of the last talk, was you can address things like hook errors. So it's important how you schedule your syndrome extraction circuit, and how you schedule your C0s, for example, in the surface code, to not propagate errors in a bad way. So for example, an X error that occurs between the two sets of C0 gates can propagate to a weight 2 error, but if you do it in a careful way, then this will not decrease the distance of your code and remains fault tolerant. So there are ways to do measurements that protect your logical information, or are not bad. But they typically rely on taking advantage of the structure of the code, and they're kind of not general all-purpose methods. And this is where techniques like Shor and Steen error correction come in, because they can kind of be adapted, and they don't care as much about the structure of the code. Okay, so Shor error correction is the idea or sometimes referred to as cat state error correction, is you prepare, if you want to measure some weight W operator, you prepare a cat state of size W, and then you do this transversal C0 operation, and then take an individual readout of each of your qubits of your cat state, and take the joint parity to determine the measurement result. So this would be an example of to measure a logical X in, say, the 7-qubit Steen code. But there's one serious drawback to this Shor error correction, is that it's not robust to measurement errors. Any error on one of your cat state qubits will flip the measurement outcome, and so that leads to an overhead in the terms of the number of repetitions you have to do in order to get reliable statistics for your measurement outcomes. And so you get this blow up in terms of the number of rounds you have to do. And this blow up, and as the larger the weight the operator is, the more repetitions you have to do. And if we're talking about measuring logical operators, these are typically high weight operators that we're measuring. So that's why Steen error correction came about, and it's a kind of more efficient way of doing this in terms of time overhead. And the idea there is, so if we're considering CSS codes, we want to take advantage of the fact that we have a transversal C0 gate, as I mentioned earlier, for CSS codes, where the transversal C0 across all n qubits in your CSS code, it acts as a transversal C0 gate on your k logical qubits. So for example, in the 7-qubit Steen code, you could prepare some auxiliary state in the 0 state, and then do this sequence of transversal C0, and then you measure out the individual qubits of your auxiliary state block state, and then take the joint parity measurement of those measurement results in order to get your measurement of in this case would be a logical Z operator. And this is really nice, because now you are no longer limited by measurement errors, because not only do you get, by taking the joint parity, do you get the result of the logical operator, but you can also read off syndrome information because you have all of these individual measurement results, and then you can look at the syndromes of the code as well. And so you can identify measurement errors or data errors in order to correct for them and infer the right measurement result. So in a sense, this is single shot. So this is really nice. So And on top of that, in cases when you have a single logical qubit, typically preparing logical 0 and logical plus is quite easy. What you do is, often we think about this in the service code, but it applies to CSS codes in general, is that you prepare like the all 0 state, all your physical qubits in the 0 state, or all your physical qubits in the plus state, and then you measure the complementary set of stabilizers to stabilize your code. And yes, this might take some time, d-time, for example, in the surface code, but you do this in an offline manner. And then once you've prepared your resource state and it's ready to go, you just do your transversal C0 gate, read off the measurement results, and then you've done your logical measurement. Okay, and this will be generally true for any CSS code with a single logical qubit. Where things get tricky now is when you have more than one logical qubit. And you could do the same thing. You could prepare the all 0 state, all plus, measure the stabilizers. But what you would end up with is the 0 tensor k or plus tensor k state. And so when you did, for example, this is an example of the 422 repetition code. I've prepared a logical 0, 0 state, and I do this transversal C0. What you'll end up measuring here is Z1 and Z2, which is, if that's what you want to measure, that's great. But the question now becomes, what if you wanted to measure Z1, Z2, but didn't want to measure this, for example, Z1 or Z2? And this comes back to my slide at the beginning, when I wanted to do these joint parity measurements, entangling measurements, it's important that I don't get the individual information about the individual logical operators. I want to get some joint parity across the logical operators. And then, so in order to do that, you would actually have to prepare a different type of resource state. And you have some stricter requirements on your resource state preparation. And typically, you can do that, and you can either do some form of concatenation or distillation in order to prepare this resource state, but that comes with some other overhead associated with it. So it'd be nice if you could just do this in a more direct manner. And this is the idea behind homomorphic measurements, is that we're going to prepare an auxiliary code that encodes a single logical qubit. So in the previous slide, that extra code block encoded 2 logical qubits, but we want to prepare an auxiliary code that encodes a single logical qubit, because then we can take advantage of the fact that we can prepare in that auxiliary code a logical 0 or a logical plus state, and then we're going to map from the logical X or logical Z on that auxiliary code onto the targeted logical X or Z joint parity operator on the data code. So maybe there's a nice schematic way to see this. So if I have some general NKD CSS code, that in this case we have k equals 3, and say I wanted to measure Z2, Z3, but I didn't want to measure Z2 or Z3 individually. I could prepare some auxiliary code here, which might have like a different shape, as a different blob, might be of different size. And then you can do a set of C0 gates, which define some mapping gamma, where the data qubits are going to be the control qubits, the auxiliary patch will be the target qubits. And the idea is that you want in this auxiliary patch, you want it to only have a single logical qubit, and it's, for example, logical Z representative here kind of maps onto the logical Z representative of the data block. Okay, so at the high level, what's happening is we would prepare a logical 0 state for your auxiliary code, and the requirements we have for the homomorphic measurement is that the X stabilizers from the data code have to get mapped onto X stabilizers in the auxiliary code. And this just is follow the flow of the C0 gates. Remember, controls on the top, targets on the bottom. So poly X flows down, poly Z flows up. So you want X stabilizers on the top to get mapped onto X stabilizers on the bottom, Z stabilizers on the bottom on the auxiliary patch to get mapped to X stabilizers on the top. And if we want to extract, for example, this logical Z2, Z3, we want the Z logical operator on the bottom code to get mapped onto the Z2, Z3 on the top. Okay, and then in order to read out our logical Z measurement, we just read out everything projectively in the logical Z basis in the auxiliary code block, okay? And you can translate these set of conditions that I wrote in words into a set of conditions on the parity check matrices, which were nicely summarized in the last talk. So you have some set of these are the joint parity check matrices for both the data and auxiliary code blocks. And you have some mapping gamma, which is inferred from the C0, the structure of the C0 gates in your mapping. And this gamma is going to modify the stabilizers of your code. And what you want is that, so you notice in, like, for example, in the first equation, the hz prime was kind of mapped onto the data code block, and you want those new set of stabilizers in the bottom left, those to be a subset of the stabilizer group in the data code block itself. And this imposes these following set of algebraic conditions. And so these are the algebraic conditions that define kind of a valid homomorphic measurement. And why we call them homomorphic measurements is that when you go through this mapping, it results in a chain homomorphism between the two sets, between the chain complex that defines the data block and the chain complex that defines the auxiliary block. Okay, so maybe if the last few slides were a little confusing, maybe I can summarize all this with a few examples. Okay, so first basic example is one we've already seen, and that is Shor error correction. So say we had a Tor code on the bottom, and we wanted to measure one of its logical qubits. So this, Tor is periodic in both directions. Well, we could prepare this rotated cat state, and we could just do a series of C0 gates, and what you would end up doing is mapping logical Z on the cat state onto the logical Z of the toric code, and then you could just read out, you can just measure all the qubits in your cat state, and then through the parity of these measurements, infer logical Z, and this would be a logical Z measurement. And this auxiliary code now is an M11 code, right, where M is the length of the cat state. It's a distance one code, right? It's just a repetition code, and that's why you would have to repeat the measurements, and that's why cat states where Shor error correction is not very desirable because it's a low distance code. So what could you do to increase the distance? Well, you could just widen the patch, right? And then if you define the same, if you prepared this patch on the top and you did a transversal C0 gate between the data and this patch, it would also define a valid homomorphic measurement, and now your patch is distance 3. So you get some additional protection. And so maybe you'd have to repeat the measurement a few times, but you don't have a distance 1 code. And so you can build up your protection by widening the patch, and this is a valid homomorphic measurement. Another example, suppose we wanted to measure Z1, Z2. A naive thing you could do is just take these two ribbons and widen them a little bit for the protection purposes, and ask, okay, if I do a sequence of C0 gates, will this allow me to measure Z1, Z2? You will measure Z1, Z2 if you prepared such a patch on top, but you would also measure Z1 and Z2 individually. And why is this? It's because the patch on top is an M2-3 code, right? It has 2 logical qubits. So you're going to actually learn 2 bits of logical information here. And that's what, we wanted to avoid that in the first place. We want this, we would prefer if the patch only had a single logical qubit in order to infer the measurement we actually wanted to know about. Okay, and so how are we going to prepare such a single patch? And here's where we use the notion of covering spaces. So we want to measure this Z1, Z2, which is given by some loop on the torus. We can take the universal cover of the torus in R2 and write this loop out as a string. And of course, we identify the endpoints of this string by some translation. And now if you mod out this translation, the covering space by this translation, what you obtain is a cylinder. Okay, so you have some cylinder that goes along the diagonal here. And then you can chop this cylinder to the level of protection you want. So the width of the, I'm going to impose some smooth boundary conditions, and the distance of these smooth boundary conditions is basically going to inform the distance of our code. And then you can map this chop cylinder back onto the original torus configuration. And what does that turn into? So if we started with our toric code, we want to measure this Z logical operator. We can look at this lifting up. And now we've prepared this ribbon code where I've identified the cyan boundaries and I've identified these purple boundaries. So you see this is just equivalent to a ribbon. It encodes a single logical qubit. But when I do this transversal C0 gate, and here now these transversal C0, a given data qubit can be mapped onto multiple layers here, so multiple qubits in your auxiliary block. But you'll see that the Z logical operator in the top, on these top two layers, gets mapped onto Z1, Z2 on the toric code on bottom. And so when you do this mapping, you'll projectively read out the auxiliary block by doing all X measurement, and you would actually then infer the measurement of Z1, Z2. And why this you're allowed to do, you'd say, oh, you could ask, well, you could propagate errors poorly because this C0, this one data qubits couples to two qubits in your auxiliary patch. But if you look at the patch itself, those two qubits are far away from one another in the patch. So you actually don't reduce the distance of your code by doing this technique. Now, yeah, there's some caveats. If you had too many layers, then maybe you wouldn't have a threshold for the top part. But in terms of pure distance fault tolerance, this should be okay. And so then measuring, as I said, measuring out the auxiliary patch allows you to measure Z1, Z2. Okay, and this type of technique will generalize to other forms of 2D topological stabilizer codes. In particular, I think a really nice application would be to these hyperbolic lattices, where there you can have much larger number of logical qubits. And instead of it just being basic translations that you're modding out here when you do this, when you do this mapping, that you're going to be looking at generators from the Coxeter group. This could be a very nice application for these results. And now coming back to this result from the Sydney group here, what are the pros and cons when compared to their technique? So one pro for the homomorphic measurements is that all of this, your auxiliary patch is prepared offline, right? And so you prepare, you do this offline preparation, you bring it, you do this transversal C0 gate, and then you measure out. And so you don't have this waiting, online waiting of D rounds. So that's nice. There could be some advantages for decoding because you can, you're not stitching things together, in which case you don't have to necessarily decode things when you kind of, when you're stitching together this surface code patch to the tannograph of some general code, you'd necessarily have to jointly decode things. Well, we could decode our patches separately. There might be some downside to doing that, though. But the big downside of the homomorphic measurements, which is not present in this other result, is that we can only measure operators as far as we know, only measure one type of logical operator. So like XX, ZZ, or XXX, ZZZ, but it's all X or Z. And this has to do with like the flow of information, like the flow of your X's or Z's. Well, they could measure joint X, Z, so there's more flexibility in what logical measurements you make. This definitely does not replace their technique. I think it's just these are complementary techniques. And I think as we think more and more about how we're doing these forms of logical measurement or computation in general, just having extra tools in the toolkit is beneficial. Okay, so I think I just went over kind of summarizing what this was about, but in terms of open questions, as I mentioned, it would be great if this technique could be generalized to measure combinations of logical X and Z. Whether it could be this is probably related to whether it could be generalized to non-CSS codes in general. And then we gave some examples that were related to where this could be applicable to 2D topological codes. But how do we adapt this scheme to more general LDPC codes, that are not non-topological? This is an interesting open area of research, and you probably have to know something about the underlying structure of these codes. but it would be nice to know if these techniques could be generalized. So thank you all for your attention.
Thank you, Thomas. I have a quick question on the last bullet point, actually.
Sure.
So when you introduced these ribbons that were slightly wider, do you think that if you did generalize this to QLDPC codes that were expander codes, you'd have to include like an exponentially growing number of qubits as you make the ribbon wider?
Yeah, that's a good question. Yeah, it could just be that as the ribbon grows, you might just, the size of these blocks might be proportional to like the size of the code itself, which could be a drawback. I think importantly, you would, where it requires some nuances, you don't want to, when you widen these ribbons, start bringing in other logical operators. You still want it to only be a single logical operator. So if you start kind of widening it too large, other logical operators might creep in, but yeah.
Hey, Tomas, great talk. I was wondering if you could comment on your ability to perform these in parallel, because it appears that you're having to keep the measurement fault tolerant means that the size of your ancilla is already quite big. So if you want to maintain limited overhead, then you're restricted to performing limited number of measurements at any given time, so you can maybe measure a constant. But can you change the ancilla code that you're bringing in to perhaps do measurements in parallel?
In theory, yeah. If you could measure, you definitely could measure things in parallel. I don't want to. Hard to say how generalizable this is, but for example, if you had one thing you could naively think of is if you had some like torus with multiple holes, you could think of bringing in ribbons to measure like some combination of holes 1 and 2. You know, logical operators are around these holes, and then you could do the same thing for at another part of the lattice, and maybe even if they overlap. So I think you can parallelize to a certain degree, but I don't know like how generalizable it is. You know, if it's fully parallelizable.
Andrew here.
I need the microphone for okay. Yeah, great talk. Thank you very much. You mentioned that if you wanted to measure a high weight logical poly operator, that might impact the threshold. Could you elaborate on that a little bit? Like, is it like the number of terms, you know, would impact the threshold linearly or something like this, or reduce it? What did you mean by that when you said that?
Oh, I think what I meant is that, you know, in the previous example here, I split up into 2 layers, right? And I had, for example, if you have an X error on the data qubit that's coupling to those 2, you know, it's going to spread to the 2 individual layers. Now, the points on that ribbon, they're far apart from each other, so it doesn't decrease the distance of the scheme. But, you know, if you had many layers here, then you have single errors propagating to multiple places. And so this, in theory, this would be bad, right? Because you could see how it could affect the threshold, because you have, but
you know how it's, that's what I was wondering, if you know how bad it is. Like if I want to measure, you know, a product with 32 logical Z's, you know,
would
the
see.
threshold be like 1/32 of what it would have been if I wanted to measure just one, or is it much worse than that?
Don't have, I think it will depend a bit more on like what the actual logical operator looks like here. And so loosely, I mean, I don't know how this generalizes. I don't want to make a statement that's wrong, but you know, here the reason we have 2 layers is basically because the logical operator has this crossing, right? And so if you wanted to measure some general operator that had many crossings, I can imagine then you would end up having many layers. Whether it's directly related to the number of crossings, a bit less clear. But in general, if you know, for these topological codes, the fewer crossings probably it won't really affect the threshold too much, I would say. Or I don't.
Yeah. Okay. Last question.
So when I think about covering spaces, I think about the code being kind of symmetric. But if we're to go beyond like topological codes, kind of, it seems like expansion might be kind of difficult to be compatible with the covering spaces technique. Do you think that's the case, or is there some generalization there?
Yeah, I don't know if I have maybe we could discuss this offline. I don't think I have an easy answer to that question. Thank you, though.
Okay, so I'm going to hand over to Stephen because he's got a announcement about the group photo. Before I do, can we please thank Thomas again and all of the this morning